Good morning. We finished that last worksheet, so now we're on to something new. But I think before I hand this out, I want to give you guys an exercise. How well do you know your reactions? And by that I mean, there's two ways to think of it. How well do you know your reagents? What reagents have we learned so far and how are they used? And how well do you know what functional transformations are allowed? What functional groups you can create from other functional groups? What do you think? Where are you at? 100%, 90%, 50%, 10%? 10%? With resources in front of you, 60%? Higher? Because your resources, I don't expect you're just going to get it one day and have all of the reagents down. But those resources are important, which is why I've been handing out these worksheets that have the reagents and the transformations. So if you have them, or if you remember where they are on Canvas, I want you guys in, I think for now we can just do 2 groups of 3. Unless you want to do one big group, 2 groups of 3. See if you can figure out all of the different ways that you can make aldehydes and ketones. When one of you finds one, or if you find a resource, then point it out to the others. But see if you can come up with a number. How many different ways can you find to make aldehydes and ketones? Your time starts now. I'm not giving you a time limit, but
I know there's 2 ways of alkynes.
I'll keep a tally for you guys. Justice says at least 2 to begin. Just shoved it in there a little too quick.
Yes, I never do that.
There's 2 ways of alkynes using the HgSO4, and then the other one is the BH3. Can't you just do reduction and oxidation too?
Well, which one? Because reduction and oxidation are opposites of each other, so. Touche. Depends on what you start with. How oxidized is it? Maybe you can reduce it down, because carboxylic acids are more oxidized than aldehydes. So are esters. But do you have a way of making an aldehyde or ketone from a carboxylic acid? We do? Okay, so a two-step process. Reduce it completely and then partially oxidize it. Wouldn't it be nice if we could just partially reduce it instead of needing to fully reduce it to an alcohol and then oxidize the alcohol further? Well, I don't think it's one that we've learned yet. That's what I'm saying. So I'm thinking one step. Well, not one step as in like the hydroboration oxidation of alkynes that you mentioned is 2 steps. So, but that's just like one conversion. Nobody would stop after just hydroboration. But try to limit it from, yeah, wouldn't it be nice if we could limit it to just one reduction instead of having to fully reduce, partially oxidize. So we've got 2 oxidation and reduction, maybe 4.
Using like an alkene and then doing like O3 DMS.
An alkene and ozonolysis, yeah. Good point. Oxidative cleavage of the double-double bond. Double-double bond. Carbon double bond. What about with aromatic rings?
Like the radical oxidation.
Well, yeah, that would fit under oxidation. That's a good point. But I mean a way of taking things that are not aldehydes or ketones and making things that are aldehydes or ketones that involve a reaction with an aromatic ring.
The one, what is it? Using like AOCO3 and using like a chlorine, like some type of, I don't know what even to call this.
We do have names for all those reactions. All the EAS reactions have a name.
The fetal cracks, right?
Yeah, that's the part of the name that I care less about. Friedel Crafts is just the people. Acylation is what it's doing because it makes it adds an acyl group, and specifically it adds a ketone or an aldehyde. So we can acylate our aromatic rings. That was something we learned this semester. Alkynes and alkenes, something from last semester. Oxidation was something from this semester. So there's not a lot of new stuff to aldehydes and ketones. Or what I should say is there's already a lot of things we're familiar with aldehydes and ketones. So now we have a new packet. And once again, I've highlighted the reagents on here. So if this is a study tool for you, good. I just uploaded this to Canvas if you want to check. You're welcome. On here, we have hydration of alkynes. And I want to point out a few things. Remember that alkynes can be terminal or internal. And I think that for some of you, you actually might not have learned about alkynes at your OCHEM 1 institution. A terminal alkyne is one that terminates the carbon chain. So it has at least one sp-CH bond. An internal alkyne is fully contained within a carbon chain. Internal alkynes cannot form aldehydes because the hydration, adding H and OH across a pi bond, the hydration will never place an oxygen on a primary carbon. There is no primary carbon. So no matter the reagent, both reagents give ketones. It doesn't matter if you're using Markovnikov hydration, which is your oxymercuration on the left, mercury sulfate and sulfuric acid in water, or if you're using hydroboration oxidation. Both of the reagents give ketones. It doesn't matter. But on a terminal alkyne, oxymercuration gives a ketone, and hydroboration oxidation gives an aldehyde. Another way of saying this, terminal alkynes have regiochemistry. They have a more substituted and less substituted carbon. So the reagents play regioselective roles. Does it put the oxygen on the more substituted carbon to give a ketone, or does it put the oxygen on a less substituted carbon to give the aldehyde? Internal alkynes have no regiochemistry. So there is no Markovnikov or anti-Markovnikov. The one that you see at 12 o'clock on your roadmap is ozonolysis or oxidative cleavage of alkenes. I want to point out the reducing agents. This is considered reductive ozonolysis. Reductive ozonolysis is distinct from oxidative ozonolysis in that your products remain more reduced rather than more oxidized. And as we just mentioned, carboxylic acids are more oxidized than aldehydes, despite both being primary carbons, so we need reductive ozonolysis here. Our reducing agents DMS becomes DMSO, dimethyl sulfide becomes dimethyl sulfoxide, and you can see how the sulfur is taking on the oxygen. The sulfur becomes oxidized, thereby helping keep the cleavage more reduced. Or we have zinc. Zinc can serve a role and helps to remove extra oxygen by becoming oxidized as well. Those were from OCHEM 1. Those were from our reviews at the beginning of the semester. Then we saw oxidation of alcohols this semester. The only one that I didn't put on here was methanol being oxidized into formaldehyde. But you have an example there that shows a primary alcohol being oxidized to an aldehyde, and a secondary alcohol can be oxidized even with a strong oxidizing agent to a ketone. And I want to have you guys stay familiar with these abbreviations. This abbreviation, CHO, is for the aldehyde. this abbreviation, oxygen in the parentheses, helps you indicate a ketone. Okay, but there's a couple of other oxidation of aldehydes, of alcohols that we did, like we did oxidative cleavage of a vicinal diol, and we saw selective oxidation of allylic alcohols and benzylic alcohols. So you guys see those on the right-hand side. And then the other thing that we had mentioned, acylation of our aromatic rings. Good morning.
Thank you.
You're welcome.
Thank you.
Of course. All of these are what I refer to as previously seen reactions. And I refer to those as previously seen reactions because they're reactions we've previously seen. So everything on the top, previously seen. Now these reactions on the bottom are new. And I do want to say, Justice, I didn't put on here reduction because that would have been like a two-step process for us. So we talked about how we can form aldehydes and ketones by oxidation. But there is a new reaction that lets us do this partial reduction that I was talking about. What you guys can see there is carboxylic acid, primary carbonyl, ester, primary carbonyl, amide, a primary carbonyl, the acid chloride, the acid anhydride, all primary carbonyls, and then the nitrile. And the nitrile carbon is also basically a primary carbonyl. All of them are reduced to an aldehyde using this reagent, dibol. Rhymes with eyeball. So what is dibol? And why is dibol able to take all of these primary carbonyls and create an aldehyde? Because the other reducing agents we've seen so far, we saw lithium aluminum hydride, LAH, which takes all of these carbonyls and reduces them down to a primary alcohol. That's not how far we're going with this reaction. All the way to a primary alcohol is a further reduction. This is only doing one part of that reduction. So what is it about dibol that facilitates this? Dibol stands for diisobutyl aluminum hydride, or aluminum hydrogen. You can see how it's written out with that dash between aluminum and H. And I hate to say it, but I've seen places where they will write the AL with a capital L, which is silly because that's aluminum, and aluminum doesn't have a capital L in its name, lowercase l. All right, so let's compare dibol to LAH. well, sorry. Differences include far less hydrogen per aluminum, and also those two big bulky alkyl groups. So the big bulky groups is going to ensure that aluminum doesn't really mess around for too long. It's not welcomed in tight environments like around carbonyl carbons. Also, the fact that it only has one hydrogen means that it can only do one reduction. LAH can do 4 equivalences of H- reduction. It can add 4 equivalences of hydrogen. Whereas dibol can only do 1 reduction. So sometimes you don't want to take a carboxylic acid all the way down to an alcohol just to have to oxidize it back to an aldehyde. So instead, we use dibol and reduce it down to an aldehyde directly. Let's look at the mechanism for it. Good morning. We looked at the mechanism for reduction with LAH a little bit. But that was not a mechanism we tested on. This is also not a mechanism we'll test on, but I want you to see why it's able to stop just there. Do you want a picture of this before I erase it? Is dibol a nucleophile or an electrophile in the context of a carbonyl? Is dibol an electrophile or nucleophile? Is dibol a nucleophile or electrophile? A nucleophile? From where? No? Hydrogen is more electronegative than aluminum, so there's a partial negative on this hydrogen, which means that the hydrogen can take electrons and use it to attack the partial positive at the carbonyl carbon. It's not very often that we see hydrogens with negative charges, but hydrogens bonded to metals almost always have that negative charge. So dibol has hydrogen act as a nucleophile in this reduction step, acyl addition. Now, what this structure has, this also, I don't like showing this because I haven't bonded it well. The aluminum and the oxygen are balancing each other's charge. This intermediate is a tetrahedral carbon that came from a trigonal planar carbon. So we call it a tetrahedral intermediate. And it has a leaving group. It has a group that can be kicked off of the structure. Bonds to carbon can't be kicked off. Bonds to hydrogen can't be kicked off. But weaker bonds like bonds to a chlorine, or in the examples that we have, if it's our carboxylic acid, the OH group, if it's our ester, the OR group, if it's our anhydride, the carboxylic acid group. If it's the amide or the nitrile, we'll talk about how their mechanisms are slightly different. But these have a leaving group, something that can be easily kicked off of the structure. In this case, it's the chlorine. But the chlorine is not going to just leave the molecule unless there's a good reason for it leaving, something to kind of push it out, and that's the carbonyl reforming. So the carbonyl comes back, which is why, again, we call it a tetrahedral intermediate. And we get rid of our chlorine, and we have this aluminum byproduct, which is why we need that aqueous workup, because somehow we're going to need to wash away all of that aluminum waste. Reduction, one-step reduction. When we used LAH, this aldehyde then gets further attacked, and a second hydrogen is added, and brings us down to our primary alcohol. But dibol doesn't have the capacity to do a second reduction. So dibol reduces once, and then is consumed and is done. Cool? On the right-hand side, what we see for our reaction 6. Hydrolysis reactions. Can you guys interpret what hydrolysis means? Hydrolysis is It doesn't have to necessarily, well, yeah, I don't know if I'd say look for a bond cutting, but it's a reaction with water. So when water is used as a reagent. In this case, it's acidic hydrolysis. We're using H3O+. So what are acetals and imines? Well, this is just kind of a big picture. Not all of these groups on here are acetals and imines. The first group that we have at the top is a geminal diol, or a gem diol. And I hope that you can appreciate the gem diol carbon becomes the carbonyl carbon. Do you see how many bonds to oxygen that carbon has? 2. Do you see in the product how many bonds to oxygen that carbon has? Still 2. It's not being oxidized or reduced, but it is reacting the gem diol with water and converting the way that those oxygens are bonded, going from 2 OHs to just a carbonyl. This next group, if we think of this as a gem diol, then this can be thought of as a gem etherol. Do you remember I tried to name a functional group like that when we did epoxide openings? If an alcohol attacks an epoxide, we get a vicinal etherol. Here, because the alcohol and the ether are on the same carbon, geminal. But the world of chemistry would call this a different group. So the name that you'll see for this group is hemiacetal. And the word hemi, like hemisphere, and there's got to be other examples, just means half. So this functional group, the geminal ether all, is halfway to an acetal. It itself is not an acetal. But when that carbon is bonded to an OH and an OR, hemiacetal. So what does the acetal look like? If both of those groups are ethers. If the carbon is connected to two ethers, a gem diether, then the functional group is said to be an acetal. We're going to do mechanisms with acetals, hydrolysis of acetals, formation of acetals. And I do want to point out how you pronounce it. I want to say my OChem 2 professor pronounced this as acetal, which I just couldn't appreciate because that sounds a lot like acetyl. Like acetyl chloride. So I pronounce it as acetal. That al at the end, like aldehyde, we pronounce that al as al all the time. Butanal, benzaldehyde. So I pronounce this as acetal, not acetyl. But do you guys see something in that name, acetal? Anything familiar? Justice? Yeah, that root that we gave for our 2-carbon carbonyls, acetic acid, methyl acetate, acetaldehyde, acetone. It still has that same prefix. And again, I have no idea why they thought that was useful. And this time, its suffix is an aldehyde, and this functional group is far from an aldehyde. So I do want you guys to be aware, sometimes the words they choose feel like they should have meaning, even when that meaning doesn't seem to make sense. So just be comfortable with the idea that it looks like it should have meaning, even if you can't figure it out. There is a version of the acetal that IUPAC is trying to bring back. And they're trying to bring back the ketal. And this really rubs me the wrong way. The distinction that they want to make for acetals and ketals, they want ketals to have a carbon on both sides, but they want acetals to have at least one hydrogen on one side. Okay, so IUPAC is saying there's a distinction between the acetal that forms from an aldehyde carbon versus the acetal that forms from a ketone carbon. But the name ketal clearly includes ketone in the front, but includes the suffix for aldehyde. It makes no sense. It's terrible. So you won't see me using this term. I doubt you'll ever see anybody ever use that term. But I do want you to have an awareness of it. You're welcome. Okay, a few more of those groups as we go down that list. A double bond to nitrogen, when that nitrogen has an OH coming off of it, is called an oxime. A double bond to nitrogen, when that nitrogen has some nitrogen group coming off of it, is called a hydrazone. A double bond to nitrogen, when it has just a hydrogen or a carbon chain coming off of it, is called an imine. Different than amine by just a letter, imine. And an alkene bonded to some nitrogen group is called an amine, which is literally the combination of alkene and amine. It's an amine bonded to an alkene. So I called this hydrolysis of acetals and imines. I'm including gemdiol, hemiacetals, and acetals in the hydrolysis of acetals. I'm including oxime, hydrazones, imines, and enamines when I say hydrolysis of imines. Because you see the similarity, correct? We've got these oxygen groups. And I'm just calling those the family of acetals, whether that's good or bad. And then we have double bond to nitrogens and a variation of that. And I'm just referring to all of those as imines and kind of imine derivatives. They all do the same thing. If I replace this R group that I have on the right-hand side, if I replace R with H, they all hydrolyze to acetaldehyde. If I swap the R group with pH, they all hydrolyze to acetophenone. Whatever that R group changes into doesn't matter. All of these functional groups hydrolyze into either an aldehyde or a ketone, depending on what's connected at that central carbon, the acetal carbon or the imine carbon. Okay, questions so far? Good stuff? Great. On the back side, we've got reactions with aldehydes and ketones. And I want to go through a few of these names so that we're all on the same page about how familiar we should be with them. Let's just say reduction. So we've got reduction of carbonyls, reductions of our aldehyde and ketone. But we've got reduction to different products. We have the Wolff-Kishner reduction, which I prefer to call the hydrazine reduction. Hydrazine is that H2NNH2 molecule. Hydrazine is similar to the hydrogen peroxide compound, but the nitrogen equivalent. Or there's the Clemenson reduction, which I refer to as metal in acid reduction. That's your zinc mercury with hydrochloric acid. These two reduce all the way to an alkane. And then we have our mild and strong reducing agents. Aldehydes get reduced to primary alcohols. Ketones get reduced to secondary alcohols. And because ketones and aldehydes are reactive enough, they're on that more reactive half of our table of reactivity. They can be reduced with either sodium borohydride or lithium aluminum hydride. Okay, those were some previously seen things that we could do. The first two reductions to alkane, we saw that in the aromatic section. Alcohols showed us this reduction. In the alcohol chapter, we also learned about acyl addition. So the aldehyde and the ketone can be attacked by organometallics. Or they can be attacked by cyanide. Organometallics increases the degree of substitution. Primary, or an aldehyde gets attacked to become a secondary alcohol. A ketone gets attacked to become a tertiary alcohol. Cyanide can do acyl addition. That gives us a cyanohydrin, geminal cyanohydrin attached at the same carbon. Those were all the reactions we saw previously how to do. So all the rest of these become new reactions. When you hydrate a carbonyl, you add H and OH, you add an equivalence of H2O across the carbonyl. You can do hydration in basic conditions or acidic conditions. What do you get? Take a carbonyl, add water across it, form a geminal diol. Keep in mind, this is just the reverse of what we saw on the front side. Geminal diols can be hydrolyzed back to their carbonyls. Carbonyls can be hydrolyzed into a geminal diol. This is an equilibrium reaction. The distinction between forming a hemiacetal and forming an acetal often comes down to the amount of alcohol present. If a carbonyl interacts with one equivalence of alcohol, then only one equivalence of ROH can be added, and instead of using H2O to add across the carbonyl using ROH means I don't get a gem diol, I get a gem etherol. One equivalence of alcohol gives a hemiacetal. Two equivalences of alcohol gives an acetal. The hemiacetal is an intermediate on the way to forming an acetal. This should make sense. In order to add 2 equivalences, I have to start by adding 1 equivalence. And it's the second equivalence that converts the hemiacetal into the acetal. It's kind of like how when a primary alcohol gets oxidized to a carboxylic acid, the primary alcohol gets oxidized into an aldehyde, and then the aldehyde gets oxidized into a carboxylic acid. And the only other thing I want you to see here is diols give cyclic acetals. The way that I've drawn this on your worksheet is I haven't specified what size the carbon chain has to be for the diol, and then I don't specify how large the ring is. So I want to give you guys an example, 2 very common examples. If my diol is ethylene glycol is this essentially the smallest diol that we'll make or we'll use, 1,2-ethane diol. The 2 oxygens become a part of the ring, bonded to the same carbon, with the ethane chain connecting them. So that's a total of 5 members in the ring. So this acetal, geminal diether, this acetal has 2 ether groups that are also just connected to each other. There is no distinction between using 2 equivalences of alcohols or having the 2 equivalences on the alcohol. The only thing that changes is whether you have 2 distinct R groups or whether your R groups are connected to each other. The other common reagent is propane 1,3-diol. Here, there's an extra carbon connecting the oxygens, which means there will be an additional carbon in the ring as well. 6-membered acetal ring instead of a 5-membered acetal ring. Those ring sizes can vary, which is why I wanted to give you a more generic version on the table. I wanted you to have something that was easily applied. Hydration of a carbonyl can happen in acid or base, but the formation of our acetals only done in acid. All right, and then the formation of imines and the others. Notice that they all are done in acidic conditions. Notice that there is no distinction between what is coming off of the nitrogen and whether it forms a double bond or not. They all form double bonds to the carbonyl carbon, except for the last one. So NH2OH, NH3, NH2NR2. These reagents all have a nitrogen with 2 hydrogens that can be lost. Plus, their reaction with the carbonyl carbon includes an oxygen that can be lost. And all of these have a byproduct of water. the nucleophilic nitrogen has 2 hydrogens to be lost, then an equivalence of water is kicked off. Actually, there's one more version. I'm not sure why I wrote it this way. That was a silly way to do it. So that includes ammonia and primary amines. But what happens if I react everything in the same conditions, but I have a secondary amine, a nitrogen that does not have 2 hydrogens to lose, a nitrogen that cannot contribute both hydrogens of the byproduct water? The secondary amine can't react like the primary amine or like ammonia, and instead has to take an extra hydrogen off of the alpha carbon. So that molecule of water is still a byproduct, but instead of getting both hydrogens from the nitrogen, one of the hydrogens has to come from the adjacent carbon. Hydration, taking a carbonyl and making a gym diol, is easily reversed by having a gym diol in acidic water. That was equilibrium based. Forming acetals requires alcohol in acid, but when you have an acetal in the presence of acid and water, hydrolyzes acetals back to carbonyls. This is equilibrium based. To form the oxime, the imine, the hydrazone, we need acid and these reagents, but when we form the final product in the presence of water and acid, they get hydrolyzed back. So these are all equilibrium-based reactions, meaning if you're aiming for 100%, you might not get there. But it also means that you can take a carbonyl, convert it into one of these groups, do some chemistry, and then convert it back out of one of those groups. Use an amine and acid to form an imine, and then hydrolyze the imine back to the carbonyl. Okay, a few more reactions that are new to us on the bottom. The reaction that goes straight up is the Wittig reaction. That's a German name, so it's pronounced like 2 V's, which isn't that the way it's written. It's written like 2 V's more than it's written like 2 U's. The Wittig reaction is considered an alkene metathesis. Do you guys know what that word means, metathesis? It means the building of. I guess it's just kind of another way of saying synthesis. Isn't that wild? That you can create an alkene, a carbon-carbon double bond, by using a carbonyl precursor and this new reagent. This reagent is called the ylide. Oops. So the ylide is a carbon phosphorus double bond. And whatever R groups are attached to the carbon of the ylide, those R groups just become part of the new alkene that's formed. So let's think about the partial charge on the ylide for a minute. There's actually a resonance form that the ylide shows. But I wonder if you guys know the electronegativity. Which atom do you suspect is more electronegative, carbon or phosphorus? This is a tough one because carbon is a row above phosphorus, but phosphorus is in the column to the right of carbon. So they're kind of in both directions of the trend for electronegativity. Turns out carbon is more electronegative. So this double bond can actually be thought of as a negative charge on carbon and a positive charge on phosphorus. And I want to demonstrate what that mechanism looks like then. So in this example, I'll use a dimethyl ylide. You know what? It doesn't need to be, and we'll use 2-butanone. Remember that the oxygen of the carbonyl is nucleophilic? Well, now we're also seeing that the carbon of the ylide is nucleophilic. So I have 2 nucleophiles, which means I must have 2 electrophiles as well. The nucleophilic carbon of the ylide attacks the electrophilic carbon of the carbonyl. And at the same time, the nucleophilic oxygen attacks the electrophilic phosphorus. And this creates one of the coolest shapes in organic chemistry. It gives us this square intermediate, where oxygen and phosphorus have bonded to each other because oxygen attacked phosphorus, and where our 2 carbons have bonded to each other because the ylide carbon attacked the carbonyl carbon. That's obviously not an alkene, so the mechanism is not done. We do need to form an alkene, which has to happen between these 2 bonds. Electrons, I don't know why I said between these 2 bonds, between these 2 atoms. We need more electrons at this bonding region. Where can I get electrons to create a double bond? Well, these carbons already have octets, so the electrons that are used to make the carbon-carbon double bond have to come from this system somewhere. It can't come from the CO bond because oxygen owns those. I did forget something in my structure. My 3 phenyl groups. Oxygen owns the CO electrons, but who owns the carbon-phosphorus electrons? Carbon does, because as we saw up here, it's carbon that holds that negative charge. So carbon takes these electrons to form the alkene. Meanwhile, oxygen takes the CO electrons and forms a phosphone. Congratulations, you've now formed an alkene from a carbonyl. We've done the opposite just on the front side. We took an alkene and we cleaved it into carbonyls. Now it turns out that we can reverse that process as well.
Is that a mechanism that you want us to know for testing?
I used to test on that. I haven't in a while, but I have put it in bonus questions before. So there is the possibility that you see it again, but I don't think that it's a mechanism I have on your learning objectives sheet. But how can you look at that process and understand how it proceeds? Here's your mechanism. Okay, a couple more. Oxidation of aldehydes. We actually have talked about this already. The fact that the aldehyde is an intermediate in the strong oxidation of a primary alcohol means that we can just take aldehydes and oxidize them further. The oxidation of the ketone, though, is different. This is called the Baeyer-Villiger oxidation, and I don't know if I will spell their names right. What change do you see happening on that reaction to the left? Starts with a ketone and becomes not an ether, an ester. So it is oxidizing the ketone because you're adding an extra oxygen to the carbon. This reaction selectively oxidizes the more substituted carbon. That's why in the example that you see, which I believe has this R group, we don't oxidize the carbon on the right, which is a primary carbon. Instead, we see oxidation of the carbon on the left, which is a secondary carbon. That's the Baeyer-Villiger oxidation. And it uses an old friend. It uses a peroxy acid. The same reagent that we used during epoxide formation, MCPBA, is used to oxidize that carbon, oxidize the ketone into an ester. Okay, and then the last one. Reduction with dibol. Well, what the heck? Didn't we just have this on the last side? How come I didn't put this one on the last side, on the front side of this sheet? Because on the front side, we used dibol to create an aldehyde and ketone by doing a one-step reduction, just a partial reduction of those highly oxidized carboxylic acid and derivatives. However, here, we are not making an aldehyde. Because when you start with an aldehyde and reduce it with dibol, you still do a one-step reduction. What I'm trying to point out is that dibol is still reactive to aldehydes and ketones. They are useful to form aldehydes, but it is just as strong of a reducing agent as ever, and so it still reacts with aldehydes and ketones. If anything, that's just a word of caution. You have to make sure that if you're using dibol, there are no aldehydes and ketones, otherwise you'll reduce those as well. All right, that is all of the reactions. I want I want to hear your input on how we spend the last 30 minutes of class. Do you want the last 30 minutes to practice applying these? Going through the roadmaps, fill in the reagents, fill in the structures? Or would you rather see the mechanisms? Otherwise, we'll do mechanisms tomorrow. I've got 1 reagents, 1 mechanisms. What? Okay. I think it makes more sense actually to do the roadmaps. Now that we've gone through all these reagents, I want you to get more familiar with them. I encourage you to work in groups, to talk with each other, to collaborate, do some teamwork. As one of you addresses what change you see, have somebody else find the reagent. As one of you sees a reagent added, somebody else looks for what that reagent is used to do. I'll come around in these next 30 minutes and answer questions and help you get through this. And then I think maybe I'll post a key for this. Maybe I'll have time at the start of class tomorrow, I can put up the answers. Okay, have fun. Those desks look so comfy though, I don't know. Mm. Oh, I should say there are some reactions in these roadmaps that are not new to this unit or even just specific to aldehydes and ketones. There's a few that are older ones that I want you to still remember.
This one, is it just, is the pH, would that just take the place of the R2?
Well, it depends, because R2 means 2 things. So are they both pH? Is it pH2? Is one of them pH and the other is something else?
Would it be NHPH?
Right.
Okay.
Whatever 2 groups you see attached there, those stay, or those must have come from the starting material. Good. No, don't worry. Do it.
Dog is having puppies.
Oh, fun.
So I'm like, is there another one? Like what's gonna pull this oxygen off?
Pull it off. That's one way to look at it. What's another way of describing that change you're seeing?
It's getting replaced with technically 2 hydrogens.
Mm-hmm. And against all the names that we gave today, that would best fit under what?
Reduced?
Yes,
I had to think of oil rig.
that's great. That's great. It's being reduced. Or you can think about how people abbreviate reduced with H in brackets. So when you increase the number of H's, you're reducing it. So now you know that you just need to limit your reactions, narrow your reactions in on reduction reactions. And if you can describe the change even more clearly, reduced to what? Reduced to an alcohol, reduced to an aldehyde, reduced to an alkane. Now you should be able to find a reaction that follows that transformation. Is this yours? Oh, I didn't erase one of my structures. Oh, man. On the back side where I gave you guys blanks to draw in the structures, that top left box has the structure in it. Dang it. Yeah, that's a freebie. Don't worry, that won't happen on the final. Take a look at some of what you've done. This is great. And this is very close. When you look at the way that we write the reaction, or what we predict, there should be, well, sorry, this is a bad example. This nitrogen that is double bonded to the carbon, that nitrogen has 2 hydrogens on it in the reagent, because then those 2 hydrogens can be removed. But that nitrogen has to also be bonded to another nitrogen. The way that you've written this reagent, the product that I would expect you to see ignore this if that's not what it was down there. And you had your catalyst. The H2 is removed and the nitrogen is just bonded to pH. So that's just the remaining R group. But that means that we're missing the other nitrogen and the hydrogen that's also bonded to it. So when you're working those backwards, think about just taking that carbon that we know was the carbonyl carbon and get rid of it and replace those 2 bonds with 2 hydrogens that were lost. So whatever that R group was that came off of nitrogen, whether that R group is another nitrogen, whether it's an OH, whether it's a hydrogen or a carbon chain, all of that stays exactly as it was shown, and then we just give those 2 hydrogens back. So what we missed was the NH, pH, that was also connected to this. Mm-hmm. Justice. What functional group is formed? No. No. Good try though.
It's an acetyl, right?
An acetal.
Acetal.
Right. So what do you need to make an acetal? What are the reagents that go into it? Mm. Mm-hmm. So you need a carbonyl and you need alcohols. Do you have the alcohol already or do you have the carbonyl already?
We have the alcohol.
So then we need to figure out where is the carbonyl. And as a reminder, the carbonyl carbon is the acetal carbon. The carbonyl carbon is the hydrazone carbon. The carbonyl carbon is the enamine carbon. So when you're trying to figure out the missing carbonyl, you have to first start by figuring out where is the carbonyl carbon, and then just remove the groups that were on it.
Because that's attached to the oxygen. Oh, wait.
Can you identify the acetal carbon? If you can, you've identified the carbonyl carbon. There's got to be a good way to say that.
Is it just the acetal carbon, is that just the one in the middle of the oxygens?
The acetal group is a geminal diether. Yep. So whatever carbon has two ethers is the acetal.
Okay, I see.
Sugars are a really good example of acetals. So if you have a linear sugar, I'm ignoring stereochemistry for this. So this is a linear sugar which has an aldehyde and a bunch of alcohols. And many times linear sugars will go through an intramolecular reaction where one of the alcohols attacks one of the carbons, turns that into an alcohol itself, and then creates a cyclic sugar. And the cyclic sugar has either a hemiacetal or an acetal carbon. Because here I have an alcohol adding across a carbonyl. That's the process of acetal formation. And so here it is. Here's my acetal carbon. Well, it's not an acetal, is it? It's halfway to an acetal. This is the hemiacetal. And I am skipping a step. I'm not showing the protonation step. So how do I know that is the hemiacetal carbon? How do I know it's not this one or any of these others? How do I know that's the acetal carbon? That's the only carbon bonded to both an alcohol and an ether. That's the definition of hemiacetal, a geminal etherol. But there's more ways that I can know that, because the acetal carbon was the carbonyl carbon. Here's my carbonyl carbon. It's an aldehyde, a primary carbon. That is a primary carbon. The only other primary carbon in this structure is this CH2OH at the end of the chain, which is not, it's not a geminal diol, it's not a hemiacetal, it's certainly not an acetal. So here's my acetal carbon, or in this case, the hemiacetal. Now, as you guys know, there are a lot of sugars that are disaccharides. I don't know if you guys know that. You might know that. And those disaccharides they create an acetal carbon because that carbon is a geminal diether. It's bonded to two ether groups. If you find the acetal carbon, you have found the carbonyl carbon. It has the same number of bonds to oxygen. 2 bonds to oxygen, 2 bonds to oxygen. They're just arranged differently now.
So is it, I think I already answered,
To what?
to-
Oh, yeah, yeah.
is it just formaldehyde?
Yes.
Okay.
Which is still a funny way to draw it,
Yeah.
but not wrong.
It's formaldehyde, please.
You see why?
Well, I see that is that.
Because it has 2 hydrogens coming off.
And this is gonna be, there has to be 2 of these.
You're right. It didn't clarify that there would be 2 equivalences of the alcohol, but had to be.
Okay,
Yep.
but I'm still, okay.
Okay, how about this? in the diagram, on the worksheet that I gave you, I said carbonyls react with alcohols in acid to form acetals. And then on the back side in that roadmap, I gave you an alcohol, and you had to figure out the carbonyl to form the acetal. Isn't that backwards? Don't I need to have the carbonyl before the arrow and the alcohol over the arrow? No, I don't. All I need is for a carbonyl and an alcohol to come together. It doesn't matter which goes into my pot first. I can mix whichever one after with it. It's not like a 1-2 step, right? It's just mixing all of it together.
So if there was, this was like not formaldehyde,
Mm-hmm.
and this had like, I don't know, CH3 or something,
Mm-hmm.
but it just come off
Mm-hmm.
that part.
Perfect. And what if it was acetone? It'd have 2 CH3s, and at that acetal carbon, it'd still have 2 CH3s. Which is a good practice in whatever your R groups are, just let them be. And if the 2 R groups are hydrogens, then the 2 R groups are hydrogens. Good. We got 5 minutes. Are there questions I can answer? Yes.
For this one, do we just from into, does that work?
BR2 won't be enough. We need, in addition to that, light to make the radicals. So the way that we would say it is BR2 HV. H is Planck's constant, and V is the frequency of light. So we use that as a way of saying light. You could literally put BR2 and light as well, just LiGHT. Because it's a benzylic halogenation as well, we could use NBS, which is just another source of radical bromine. But this is great. Well, actually, I would say Planck's constant is usually written as a lowercase h. If I saw that, I would give credit for it. But I want you to have that at least.
Okay, thank you.
Yeah, this is great.
Thanks.
This one, I think maybe you mean PCC instead of PPC.
Yes.
But PCC, actually this is, yeah, we show it over here, right?
Yeah.
PCC forms aldehydes from alcohols, not from carboxylic acids. What we need is a reaction that forms, starts with a carboxylic acid and forms an aldehyde.
So we could use something like, we can use this.
Good. This is a reducing agent, and the carboxylic acid gets reduced to an aldehyde. It loses oxygen to the carbon, and it gains a hydrogen. PCC is an oxidizing agent, but this is not oxidation.
Excellent.
Good. I gotta say, I really appreciate the effort you guys are putting into this, and that you worked hard these last 30 minutes, but I felt a little bored. I felt like maybe there needed to be more interaction. Like maybe I need to have you guys work on part of it for a few minutes and then swap and like work with other people and talk with each other. I don't know. What do you think? You guys are already working together. What are you shaking your head for? That's what I'm looking for, is for you guys to actually bounce ideas off each other. It's great that you're getting the practice. I'm glad that we have time to do that. But I worry that I need more, I need to be able to get you to engage more than just doing it. So I don't know, if you have ideas, let me know. I can't think of how these worksheets actually correspond well to teamwork.
But I can't teamwork on the test.
No,
So
you,
that's why
no, you
I like
can't.
to do it, but then I ask if I get stuck.
Yeah, I know. And I did see that you guys were talking when you got stuck. It just,
But like I do get why you want us to.
yeah, I want you to bounce ideas off each other as well, because I think you learn a lot through that process.
Yeah. Yeah, probably.
anyways. I guess also it was kind of a lot to do in 30 minutes. The alternative, another option I guess I could have had was if you'd finished to actually go over your answers together. You got 3 minutes if you want to do that, but I know most of you probably didn't finish all of them. And would you rather that I just post the answers to this like I posted the answers to the one we did before the midterm, or that we come in tomorrow and I just put the answers up on the board?
Do you have time to like go through it?
Right now?
No.
Probably not. I could get started on some of them. Tomorrow, maybe. Yeah. I think we could go through them.
I think if we have time it would be useful, but if we don't.
Good. Let's do that then. Tomorrow's going to be mechanisms. So we'll start with finishing these roadmaps, and then we'll go over our mechanisms. And then you guys will also have time to do your homework, to solve the mechanism for your homework and to solve the synthesis for your homework. So we'll start tomorrow with answering these. If you still need to work on them, take it home and work on it tonight. And then we'll meet up tomorrow.
I just want to say what happens with the
Oh, yes.
this.
Yes, thank you.
So this is the link, right?
Yep.
So when I click on it,
And then I think you said you've been clicking on activate.
I
But
don't
let's instead do
join course,
join course.
but it's asking for a code. Usually before this happens, I just used to click on this link,
Mm-hmm.
and that's where I come here and find all the homework, quizzes, practice, but this start popping out where it says activate your account.
Mm. Did you have an account already? Were you doing your homework at the start of the semester?
Yes, I did. So
So it kicked you out somehow.
when I made my account, it says you have 7 days
Mm.
activation.
Okay, let's see if I have a code somewhere.
I did reach out to them, but I haven't got a response.
Really, they're usually